Okay. Hello. I want to go over two tools in secure computation. One is Oblivious Transfer Extension, and one is cut and choose proofs for used for Yao's garbled circuit. Let's see if the time allows for this. Okay, so let me get my notes in order. Okay, so recall that OT used is used all over the place in multiparty computation. So we saw the GMW computation, which is OT per gate, and Yao, the garbled circuit computation, it's OT per input bit. Okay, and so OTs are equivalent to public key encryption, more or less. So you can get yes. So what we saw is that OTs you can get them from some form of homomorphic special public key encryption that has some homomorphism, but the point is that it's not known how to achieve OTs using symmetric key crypto, and there is evidence that these problems are equivalent, and they are strongly separated from symmetric crypto. So they're not going to be cheap, and you know, we've seen from homomorphic encryption, which the kind that was implied by decision RDP-Hellman assumption. Okay, there's different homomorphisms that are sometimes asked, you know, as opposed to fully homomorphic encryption. That's not what we used here. So the idea and who proposed this OT extension first? So I think it was in this paper, Ishai, Kilian, Nissim, Petrang. This how to extend OT extension, which what are you extending? So the OT extension is from K OTs, where K is a security parameter. If you just do 128 OTs, let's say, can you get any number of OTs, polynomial in the security parameter, using just symmetric crypto? So you perform the standard 128 OTs, and then somehow magically, using just symmetric encryption, you upgrade it to any polynomial in the security parameter. In particular, you know, if you have 100,000 gates in a circuit, these 100,000 gates are going to, after this 128 of essentially El-Gamal instances, you will do some symmetric operations per each gate here, hopefully equivalent to you know, symmetric encryption of some values that are hopefully also not too long, right? So another thing is bandwidth. in these applications. So in the GMW, we were just OTing bits. So hopefully, the size of the messages that you use here is also proportional to the payload that you are OTing, which was bits here and keys here. Okay, no, using OTs per input bit basically stops secure computation on large data. And the OT extension just cancels this overhead. Okay, so okay, so here is the setting. You have a sender who has his inputs are pairs of messages, and there is n of them. Okay, so so we want from k instances of OT on n-bit payloads. So we will just do 128 OTs, where the messages that are OT'd in those are n long, where n is the number of OTs that we eventually want, and these are n instances on say L-bit payloads. The L is flexible. Like some of these OTs can be on short, some of these can be on long. It doesn't even have to be set at the time when we are going to do these base OTs. So eventually the sender is going to have n pairs of messages, because this is what we want to implement, and these guys are L-bit long. Whereas the receiver will have a vector of selection bits. So hold on, let me see whether this is visible not super well. Try to focus. Okay, maybe slightly better. These are the selection bits. So Ri is the selection bit on ith OT instance. So this is the inputs to this eventual OT computation. These are the sender's inputs, and these are the receiver's inputs. And here is the OT extension idea these guys had. In a funny way, counterintuitively, we're going to do an OT. These instances will change the direction. They will go from the receiver to the sender. Okay, so the receiver picks a random n by k bit matrix. Okay, and so this is the matrix, and we are going to look at the jth row of this matrix, and the size of the matrix is here is n. Sorry, here's k. Here is n. Okay, and let's look at the selection bit vector r, which is n bit long. Okay, and the sender is going to pick his selection bits in these, we call them base OTs. these are the base OTs that we're going to do the standard OT, implement using standard OTs, like this one. And these are the eventual ones we want to implement. So the sender is going to pick a vector of selection bits that is only k long, because we are hoping to do it using KOTs. And they will run an OT in the receiver to sender direction, where the receiver is going to, sorry, sender here, who is, okay, the S is going to be the receiver on these OTs. He will use the jth bit in this vector as a selection bit. So this goes for all j from 1 to k in the k range, right? So this is repeated k times. And the messages that R is going to input into the jth OT are so the messages on this OT are equal to Tj, which is the jth column of this matrix. That's the zeros message. And the one message is the same column Tj XORed with the vector R. Okay, so he picked, this is actually eventual key material that R will use to implement these OTs, the final OTs, the target OT. And this key material R picked at random. And he uses this key material to either send it in the clear to S, if the selection bit here, if this guy's selection bit is 0, or he sends the key material XORed with his selection bits. But notice that because Tj is a random value, so this guy gets either a random vector or a random vector XORed with R, and by one-time pad, this obliterates information in the in this R, right? So the Tj is like a one-time pad. So both of these left and the right, if this guy gets only one of them, then either one looks like a random vector. Let's call the vector that this guy gets Qj. Okay. And Qj, by because this is an OT, is equal to either the jth column if Sj is 0, or the jth column XOR R if Sj is 1. The sender is going to gather all these Qj vectors in a Q matrix on his side. Okay, so he performs these KOTs, and he just sticks the outputs into the matrix. Now notice, I can write this in a simpler way. The jth row, the jth column Q is can be expressed as Tj XOR the bit Sj times vector R, right? Because this is a bit. If this bit is 0, then this thing is a 0, and if this bit is a 1, this thing is an R. Is the R, right? So you get this equation. Okay, so this is a column view of what is happening. The jth column of, okay, so now because the columns are related like this, So now I can express the whole matrix Q as the matrix T, right? Because Q is a copy of, well, each column is a copy of Tj, XOR the stuff. So let's take all these vectors and just call them a matrix. And I will call this matrix a delta, a shift matrix. This delta is computed as, well, what is the jth row of delta? Column of delta, right? It's R if Sj was 1, and it's all zeros if Sj was 0. So delta is a matrix like this, right? Like you either have R basically in places where Sj's are 1, or other columns are just an n long 0 string, right? So this delta, it's really a multiplication of the R vector times the ST, right? Because if I take this column, right, and I multiply by these guys, that's exactly what I get, right? So it's an n by k matrix. Another way to see it, right, is that delta is the entries in the delta in the shift matrix delta are well, at every row and ith row and jth column are just, I just multiply these bits. Right? Okay, so now let's switch to the row view of what is happening here, right? So this is the column view, but we have what we accomplished is, if T is a key material that the receiver chose, then what the sender gets is that key material, but shifted by a delta matrix. And a delta matrix is, you know, pretty simple stuff. It's just R's everywhere that the selection bits here are 1, and zeros everywhere else. The thing is, S doesn't know which columns. Well, actually, he does. I mean, he knows the selection bits, so he knows that a particular column he gets is TJ or TJ XOR R. But since he doesn't know TJ, this doesn't really right. So okay, but he knows that it's either TJ or TJ XOR R, and he knows which one is the case. Okay, let's switch to the row view, because in a row view, we are going to use the rows of this matrix now, and I will denote the rows using, you know, I denoted columns superscript, the row subscript. And now in a row view of this, the ith row of Q is XOR the ith row of delta is the okay, not surprised there, is the ith row of T. Okay, but what is the ith row of delta? The ith row of delta. Okay, so let's look at that. So delta is R, which is this vector, times S transpose. So the ith row of delta is, well, take the ith row of R. How did this come about? You multiply this bit by all the bits here. That's this row. So the row here is just Ri S. Okay, I'm not going to write transpose because just okay, fine, whatever, transpose. So this okay, no, screw the transpose. Okay, this is therefore either S if Ri is 1, or K long string of zeros if Ri is 0. Okay. So the dependence of columns, because the shift matrix is a product of R and S, right? This convolution. Okay, I forget what this kind of matrix product is called. And therefore, the jth column of Q and the jth column of T are related by they're either identical or they're shifted by R, XOR shifted by R, depending on the bit of S. But if I take the row view, the ith row of Q and ith row of T are related by this shift, which is either S if ith bit in R is 1, or they're identical if ith bit on R is 0. So this relation imposed by the OT, okay, turns out to be, it was created by R2S OTs, but it's a relation that is symmetric. If you view it as a constraint from R2S OTs, it's a relation on columns. But if you switch, flip the view, and now you look at the rows, then the relation is on the rows is basically switches the role of here. R was a fixed pad that is applied to the rows of T, and S was selection bit. But once we flip the view, then it goes the opposite way. S is the pad that is applied to every two rows based on the select ith bit of R as the selection bit. And remember that this is a target application. What are we trying to do here? We have n messages, n message pairs, and R is the selection bit. So ith bit is the selection bit on ith target OT. let's write, just like we had this relation on columns, let's write the relation on rows. So in the row view, therefore Qi, the ith row of Q, is Qi is well, Ti XOR delta I. Okay, I'm putting delta on that side. That's of course equivalent. And where delta I is what? Delta I is Ri times S, right? And now you see the symmetry. The symmetry is between this equation and this one. Okay, we're very okay. Like you basically see the symmetry between these. If this is what an OT instance, the base one gave you, now suddenly you have the same relation. So maybe on rows, can you use this relation to implement the target OTs that we wanted? Okay, and yes, you can, because what this means is that TIs are okay. So TIs are random keys which R chose, right? So R chose this whole matrix, and now I'm thinking of the rows of this matrix as the key material. Okay, and the rows of what S received, QIs are keys which S received in this these R2S OTs, the base OTs. Okay, that's on the surface. The base OTs implemented column transition, but of course, column transition is the transition of the whole matrix, and therefore it can be viewed as a transition of rows, and that's the relation on rows that is implied. So, and the relation between the keys that R has and the keys that S has is that the receiver key on the so these are N keys. We will use them to encrypt the target OTs, the messages in the target OT, and these are the N keys that the sender will use to encrypt. And what's the relation between these keys? They are equal if the receiver's selection bit is 0, the target selection bit. Okay, not the base OTs. So therefore, S should encrypt MI0 under what he has QI as a key. We use this row as a key in encryption. That's if selection was 0. Well, but if selection is 1, then TI is QI XOR S, the ephemeral selection bits that sender chose in the base OTs. But now, in the row view, this vector is a pad that is applied that either shifts makes QI either equal to TI or shifted by this pad S. So that's if the selection bit, if the receiver selector bit is 1. So therefore S should encrypt MI1 under well, S has the Q matrix and this pad S. So you should encrypt under QI XOR S as the key. And that's basically it, right? Because now the sender, how can he implement these NOTs? Well, for every row I, of which there is N, right? He will encrypt MI0 under QI and MI1 under QI XOR Shift S. Okay, the only problem with this is that slight problem. Keys, if I use such keys, this right, because on every N of every I used these keys which are equal to either QI, that's the 0 message key I will use, or QI XOR S. These are not 2N independent random keys. Yes, they are correlated. If QI is the random string, okay, well, it was chosen by the receiver, and it's either equal or it's equal to that Shift S. But there's not enough entropy here, right? There's not 2N independent keys. There is N keys, and then there is this one string. So any two rows are correlated, right? If you XOR the left and the right key, they always XOR to this fixed string S. Okay, so random oracle to the rescue, a perfect tool for destroying dependencies. I mean, it's a hack, really, right? If you have dependencies between keys, well, or any input really, and the only thing is that they are either same or not same, well, put them through a random oracle hash, and their output will be uncorrelated now, except if adversary can query these pre-images, right? So then, okay, then they are not secret keys because adversary will compute them. But this reduces the issue of whether or not these values are independent to whether or not adversary can compute both of them. And he can't because this S is hidden from him. Okay, so how do we encrypt exactly? S sends YI0, which is MI0 XOR hash of, well, just for the good measure, let's use the index of the row as the input to the hash function. And the zeros message I wanted to encrypt under QI, and the right message, the one with the selector bit 1, I will encrypt under QI plus XOR S. Okay. Now what does the receiver output? The R outputs. So he sends this to R, and R outputs for every I in N, right? And R outputs Zi, which is, well, he takes the ith message on the ith OT, and which one does he choose? Well, the one chosen by his ith selector bit. So it's this one. I choose Y with I and Ri as a subscript, and I XOR it with hash. Okay, he knows it's an ith instance. And what does he use as his key? Well, the only thing he has, which is TI. He has nothing else. The TI is the receiver's key material, right? So that's what he has to use. Okay, and now why is this correct? Because, well, let's see, what is this for Ri equal 0? So for Ri equals 0, this is going to be yi0, so this is mi0 XORed h of I qi XORed h I ti, but ti is qi XOR s without an XOR, because here is an Ri0. So these two cancel if Ri is 0, because recall Ti is Qi XOR Ri times S. Yes, so if Ri was 0, then Ti is Qi, so they cancel. If Ri is 1, so he took Y11. Okay, so this is Mi1 XOR, well, this stuff. So H of I Qi XOR S, and now he's going to XOR it with that thing he has, which is hash of ITI. And now if Ri is 1, then this and this also cancels because of the same equation, right? If Ri is 1, then Ti is Qi XOR S. Okay. So the final thing is secrecy. So this is correctness, right? The receiver does get what he should. Secrecy, what happened in the protocol again? Okay, so there was the OTs where this guy added TJ or TJ XOR R, and this guy added right and got QJ. So that's one thing that happened, and then there is the transfer of the YJs. And this goes over J in K, right? So the protocol has two steps, and that's what they are. Okay, so secrecy for let's say for S first. Okay, so here is the receiver, and here is the sender. Okay, so what did Well, no. So let's do for receiver, meaning what does S learn in this protocol, right? So how does this protocol keep the privacy of R? What is the R's input? Is the selection bits, right? So is this protocol hiding selection bits? So, well, this transfer, of course, there's nothing S gets. So the only thing S gets is this stuff. Okay, and because this is either TJ or TJ XOR R, and TJ is random, so I'm repeating myself now, this is a one-time pad. Yes, so it's perfect because TJs are one-time pads on R. Yes, so in other words, QJs are random independently of R. Now, what about for S, meaning what does R learn? Well, clearly learn nothing in the OTs, just by the OT property. So the only thing is what he learns here. Okay, so let's recall what that is, right? I mean, and it's here. So I can rewrite these hash queries as let's look at them from the receiver's point of view. What is QI and QI XOR S? Well, it's TI and Y0, Y11, MI1. So it's GI. Okay, no, it's actually it's not. Okay, let's see. So TI is QI XOR RIS. Okay, that's my brilliant equation. So QI, of course, is TI XOR RIS. So and QI, that's used in the for the first encryption. So this is wrong. The first encryption runs RI. Yeah, this is right. So this is QI. And the second encryption uses QI XOR S. What's QI XOR S? It's TI XOR the negated bit RI times S, right? Because I just took RIS and I XORed with S. So basically it's a flip of RIS that is acting here. So that's what it looks from the receiver's perspective. He has this random matrix P. And his selection bit R. He injected this T into the OTs, and what's coming back is messages that he would love to learn, but they're XORed with this arrow hash that uses these inputs. Well, the index is of course public, so the question is, well, you know, whatever he learns about this stuff is even only if he can query age, so he gets basically random stuff at first, right? Because the arrow means that, okay, it's unless you query, you know nothing about these paths. Okay, so he has to query on well, some path, right? And the question is, oh, sorry. Okay. Sorry. The question is, well, it's by correctness. Clearly, he knows one of these paths, right? If whatever RI is, one of these is 0. So either here S drops out or here S drops out. And since he knows TI, Well, he clearly can do this. So yes, and he will get, as we argued in the correctness, the message that is indicated by his selection bit, right? But can he query? Can he also query? Can he, can our query on I ti XOR s? Okay, because the other one is always the ti with an s as a shift. And look, he knows nothing about s. Okay, this stuff by RO is random, except when somebody queries, at which point this hash function basically patches up so that the answer of the hash is exactly the XOR between one of these random paths, the correct one, and whatever the message is revealed to the simulator, right? So think of the proof. The prover, the receiver specifies, okay, that's my bit because I'm specifying the TI at that point. And now the simulator says, okay, he chose the 0. The ideal, the function, in the ideal world, emulation, at that point, the simulator gets, okay, here was the message. You're welcome to simulate so that the receiver's view looks like an OT case where that is the message that he learns. And that's okay, because this hash function can be at that point patched to be an XOR between this chosen message, this ciphertext on the chosen index, and the message that is revealed in the simulation to the simulator. And he can do it for either case. And the other remains random unless receiver queries this, which he basically can't, because this is a random k-bit string and nothing in the view is correlated with the string. Okay. So okay, so that's the OT extension. This symmetrical flip is, I think it's truly, I mean, okay, maybe simple, but at the same time quite amazing. And these ciphertexts are as long as the messages, right? Because and if you wanted, half of them to be long messages and the other half very short, it's okay. You use a hash. By the way, you don't really, what if these messages are 10,000 bits? Do you have a random hash onto 10,000 bits? But you could construct one, but you don't need to. You just hash. You use kind of hybrid encryption. You use this hash to derive a key, and then you encrypt the long message under that key using standard tool. So, okay. And if you, conversely, if these things are very short, then sure, use, if you believe that SHA-256 is a random oracle, just hash and take, if this is 10 bits, just take 10 bits of output. Okay. So the length of this ciphertext is proportional to, is basically the length of the message, which is really sweet in the GMW case when we are OTing bits. Okay, so indeed the online computation is just 2 bits, right? For the well, in the GMW this was a 1 out of 4 OTs, so this would be 4 bits per gate. Which is pretty nice, no? I mean, of course, you want to even get over the need to interactively communicate, but that's a different story. Maybe one thing is that, well, these OTs, how long were they? So what's the bandwidth here? The offline, meaning pre-computation, was, well, the cost of KOTs. So this is some public key crypto. So this is OK group elements. Yes, but this is just a security parameter. Plus, well, the payloads. What were the payloads on these? They were the columns. So the payloads was order of KN bits. Yes, because the whole matrix. Now online, it's order of n, how many OTs you do, times L. L is the size of the the messages, right? So for simplicity, they're like they're the same size, right? So which they are in GMW and YAO. In the GMW, these are bits. In YAO, these are keys. So this is clearly optimal. It's as big as these things are that you're transferring, and that's how much bits you transfer. What about this part? So, well, if the eventual application, is that you're sending things which are security parameter or longer, then this overtakes. So this is okay if this bandwidth overhead. So this we are happy with, right? We reduced thousands of public key propositions to just 128. Okay, we don't know how to do even better, but we're really happy with this part. But we get this bandwidth of the base OTs, which are n keys. If eventually we are sending messages which are security parameter long, this is the same order as that, so it's okay. But if L is constant, let's say, like in GMW, then the offline bandwidth is k times the online one, right? And I don't remember if this is improved. Okay, maybe it is, maybe it is not. Okay, I just realized that this is a clear thing that you would like to improve, and I don't know if it has been. Okay. Do you have questions?
I'm good.
Okay. Okay. Oh, no, this reduction of polynomially many would look like a public key primitive to just security parameter instance number of instances, and then some magic and a beautiful idea, in other words, to patch up with symmetric cryptography. It raises, the same question can be raised for many other public key tools. So extensions for other public key tools. Here's one that I've been working on a bit, not on extension, but just on the tool itself. It's a very neat tool where some party, let's call it a client, has an argument, and some party, let's call it a server, has a key, where K is a key to a PRF, a pseudorandom function F, and X is an argument, and they can enter an oblivious PRF protocol. So this is oblivious pseudorandom function, where this client gets the value Y, which is the output of a pseudorandom function on his argument X. But that's the only thing he learns, right? So he gets the pseudorandom function computed correctly on his input. And by the pseudorandomness property of Fk, this leaks no information about the outputs of Fk on other inputs. Yes? So if he computed it 10 times, he can compute the PRF output on 10 arguments, but no more. And it's oblivious in the sense that the server got nothing. So there's only one thing to learn for the server, which is what was client's inputs, what is the argument on which the client computed the PRF, and the server doesn't learn. Right? So you can very inexpensive OPRF from random oracle and decisional Diffie-Hellman. So the following function is a PRF in this model. I take a hash. That hash takes bits and maps them onto a group where the decisional Diffie-Hellman holds. So I hash onto a group, and then I take this and I exponentiate it to the k. So if hash is a random, it's the random oracle. These are random group elements, and by GDH, random group elements exponentiated to a random key, even though it's the same key over and over, right? So I get some random group element, and I get this element exponentiated. I have another element, and this element exponentiated. All of this is indistinguishable from random group elements. So therefore, these outputs are random group elements, as far as you can tell, under the DH assumption. And just so that, basically, we have to hash down these random group elements back onto the bit strings, unless we want a pseudorandom function whose range is a group. And for some technical reasons, it's a good idea to also put the argument here. Now, what is the oblivious procedure for this? Super simple. So here is one. This guy sends the hash of his argument to a random exponent from this field. So this is of prime order. P is the order of this group. And this is what the client does on input X and a server on input K responds by just exponentiating this. This is called blinding, and it can be deblinded. So this guy outputs a hash of his input, and this thing deblinded. How does he deblind? He takes B to the 1 over R, right? And clearly B to the 1 over R is A to the K 1 over R, and A was H of X. So this is R times K times 1 over R. Clearly these two things cancel, right? So you get this. This is called a blinded exponentiation. This goes all the way to David Cham, who showed how to use the kind of blinding for blinded RSA for signing blinded messages. Okay, so you know, you can use it in also the privacy preserving applications like anonymous cache. Also the other applications were proposed for this type of stuff. You the server signs something, he doesn't know what it is. So it can be used as a, you know, a kind of a ticketing mechanism. The server gave you 10 tickets to authenticate, and then you use them to authenticate, but he cannot link the tickets he gave and the fact that you authenticated, right? Because he issued tickets in a blinded way, like so. This, yeah.
So in this case, the reason you're blinding is just so the server doesn't know you use the same X, because if you have age X,
Yes.
you should be able to invert it, right?
If you have what?
So let's say you didn't use R.
Yes.
Then the server would still not know X, except if you repeat X.
Well, no, but well, if he, yes, but there's a public hash function, so he can query H on any X and find your X, right?
Oh, he could.
So it's sort of subject to like a offline dictionary attack. But yes, if X was a key, then hashing X, yeah, hashing high entropy value is going to protect it, but up to a dictionary attack.
Okay.
All right. So this tool, you know, is being used all over the place. And it is also used in there's uses in MPC. So I myself use it in some password protocols, for example, where it's a single instance per password authentication. So batching multiple OPRFs or trying to do, you know, hundreds of thousands of OPRFs at the cost of just 100 is not an issue. But here is the usage of OPRF in another public key problem, which is set intersection. So this is one of the you know, most famous cases of MPC. You know, it's a flagship example people give. You know, what is the example of using an MPC? So some party has a set. Let's say a set of drivers in a state that don't know, have GUI you know, warnings, and the other has party has a set, let's say a similar database, and the SI should tell both of them what is the intersection of the two sets? Okay, so this is the MPC. This is the circuit that they want to compute. Okay, it finds intersections of. Of course, I can write it as a circuit, and MPC for this would be implied by any MPC solutions we have seen, except that it would rather be a complicated circuit. If these are n, let's say what I'm computing is nk size. So basically, I'm hashing, right? Because I don't have to compare large orchards. I can use collision resistant hashes, and they are k long each one, and there is n of them. So this is the input size of both parties. And what's the circuit? I mean, it seems like it's this size. Okay, or perhaps if you are very, very tricky, perhaps you can do it, like this, where somehow you have a sorting network which compacts, because this is a dumb pairwise comparison, right? Perhaps you can sort the whole thing and then find, basically implementing a circuit like an oblivious sort and check, right? Well, I guess if these guys pre-sorted their things, then maybe it's n time k if pre-sorted inputs. Yes, because basically it's like a merge, right? Algorithm that is. But in any event, these are pretty big circuits. So the question is, can I do this fast? Well, actually, you can with OPRF. OPRF implies a straightforward set intersection MPC, like what? Let's say, so this guy has n values in his set, and this guy has n values in his set. Okay, let this guy pick a random PRF key. Let him send the values zi, which are fk on yi for every I. So he just computes the PRF on his inputs and sends this over. Now, because it's a PRF, it tells me nothing about these arguments except that they're different. But okay, without loss of generality, everything here is, there's no repeats in these sets. Okay, so these EIs under the PRF assumption it tells me nothing about these arguments. Even if I guess them, these are inputs and outputs of a PRF, and the PRF property is that these are uncorrelated. And then for all these outputs of they run an OPRF protocol where this guy gets some outputs VI, and this is done for all indexes again. So this guy gets the set like that, right? And these are FKs on his inputs. But what did this Y player get about this? Nothing by OPRF property, right? But what did the X guy get? Well, he got the FK or computed on all his arguments. So of course he can compute the intersection. The set intersection of X and Y is the set of indexes I such that VI is in the set of these ZJs. All right. whenever this value appears in this set, it means that the Y set included Xi. Yes, and nothing else is revealed by this. So it's a rather immediate application of OPRF to set intersection. And what's the, so using the solution before, what do we get? We get n order of n exponentiations for both parties. And the bandwidth is ON group elements and ON ciphertexts. The OPRF here was, a group element one way, the group element back, and the ciphertexts are as long as the outputs of this hash, right? So these are the outputs of the PRF, so security bit. So this is this part is O and K, where K is the security parameter, and using elliptic curves, this is 2. If the group is an elliptic curve, where the size of the group is linear in the security parameter. So, but this is a bottleneck. Can we use order of sec-bar exps, right? It's exactly the same problem. I mean, the same type of problem. You have a tool that now need to, let's say these sets are big, right? Well, I have to do exponentiation for each. Okay, can I do this faster using some extension, OPRF extension? So there is a lot of works that tries to target this by not exactly batching OPRF, but doing some other bucketing, reducing this problem to shorter buckets, and driving down this part of the cost under it's beautiful work, and because, right, it might not be apparent how you improve on this. But another strain tries to create like a extension for OPRF, and forms of these extensions are known, but it's not like a perfect extension the way the OT is as of yet. So this is definitely an active topic of work. Okay, and there was no cut and choose. Just when I said that I will try to do both, I knew that that's nonsense. But I think this stuff and like the relevance to the ongoing work. I mean, an OT work is also ongoing for sure. Well, that would be an interesting side stuff. Okay. Next week is our last week, and there's lots of beautiful things we could talk about. I think the choices I see are private information retrieval, ORAM, and I would like to do something about the blockchain MPC, but maybe we just do this as a seminar next quarter, because I think that the private information retrieval and ORAM are beautiful tools and stuff that you should learn about, and I think that would be plenty of stuff for just 2 lectures that are left. Okay, so see you then.
See you.